Okay, so hello guys. Yeah, I guess I'm well. Okay. So we were discussing expanding horizons 6.0 video solution. Yeah, we were discussing expanding horizons 6.0 coding test. So this is the part 2 of that video. I have already recorded the part 1 in which I have discussed these two problems, the problem 1 and problem 2 of the contest. The problem 1 was this Aditya and Ventus treasure map. That problem was based on Cadine's algo, right? Subarism, maximum subarism. And I have already discussed this second problem, Sahil and his delusion, in which we have done was we have created the next data element and then we have created vector of set of integers in which we have stored whether we have stored all those indices. Yeah, basically v of I. This problem, let me check it again. Yeah, v of I was set of all indices where a person standing at I can go. And then I have checked all these queries in log n time. So the overall time complexity for that problem was n log n plus q log n. And I have already and also I have discussed the segment solution, which is optional for you guys, right? Check with yeah, recording is. So in this video we are going to discuss problem 3, Operation Redwire, and the problem 4, which is this. So Preet goes back to the future. Let's start with this third problem now. Yeah, Operation Redwire. Let's reread the problem. Year is 1971. The world is yours. Agent Udit and Agent Shubham is working on top secret Operation Cypher. Basically, this was just the storyline for the problem. Let's read the main part of the problem. The network is vast but broken into separate components. Okay. Basically, we have given a graph which can be which can have different components. Okay, and also your mission is to analyze the network and determine the shortest secure communication path between source base and the target base, ensuring the integrity of flag compromised wires. Okay, basically, let's see the challenge part. Your challenge is to evaluate whether these compromised wires can be safely used for communication. Okay, the shortest possible. I need to determine the shortest possible path from source to destination, that is from S to T. That must include that compromised wire. Okay, and if it is impossible, I have to return -1. Yeah, nice. Okay, yeah, take. So constraint for n is up to 10 to the power 6, and the constraint for m is also 10 to the power 6. Yeah, source and destination can go up to n. Yeah, the cost of each wire. Basically, we are given a weighted graph, and weight can go up to 10 to the power 9. No problem. Right on. Right. Okay. I got it. Basically, what we have given is we are having a graph, weighted graph, and we need to consider best path. We have uh, m number of edges, right? So we have to one by one. We have to consider each edge, and we need to answer the best path from source to destination, considering that edge being the part of that ideal path. This is the problem. Need the best paths considering all edges one by one. That is, I need to print the shortest path from source to destination considering all edges one by one. Let's see what it is saying. Okay, yeah. So I have drawn the given sample graph. It looks like something, and the source and destination for this graph was source was 1 and T was node 3, right? We have to consider somehow the shortest path from this source to this destination, and for each case, like let's say if I am considering a edge u to v of this type. Yeah, u to v with weight w, right? I need to consider the ideal path which is considered which consists of this particular edge. Let's say, as we all know, like if we have to somehow consider the shortest path from source to destination, this is a single source shortest path problem, so we have to consider Dijkstra, right? So the shortest path required considering u to v edge can be in two senses. Let's say if this is source, this is destination, and this was the edge, so the shortest path can be something like this: the shortest path from S to U, then this edge, and then shortest path from V to T. And also the shortest path can be something like this: source to V, then V to U, and then U to T, right? So in these two manners, we can have the shortest path from S to T consist of U and V, right? Okay, first see, uh, let's try to analyze that part when we have to print minus 1. As we have multiple components, let's consider some of the possibilities. If source and destination are in different component, that means different component. In that case, there can like in that case we can't find a shortest path from source to destination, because so from source a person can't reach to destination because both of these nodes are in different components. That means for this type of scenario, the resulting array should be minus 1 minus 1 minus 1 goes on up to m elements because there are m edges, right? Otherwise, there can be the case that s and t are in same component, but let's say if I'm right now considering this edge u to v, uh, and for considering a path, I am either considering this s to u distance and t to v, or I am considering this s to v and t to u, right? Let's say while considering these paths, if there is a case where this particular distance is infinity, that means source and u are in different component, or t or v in different component. In that case, the path 1, which is s to u, then u to v and v to t, this type of path will not exist, right? And if we are considering s to v, then v to u, and then u to t, while considering this type of path, if s and v are in different component, or u and t are in different component, then this particular type of path will not exist, right? So in that kind of scenarios, we will be having minus 1, right? That means we can't consider that u to v edge for a ideal path, right? We will see this situation, or we will see this constraint while implementing the code. Let's see the general scenario right now, where the edge u to v can be the part of ideal path, right? So shortest path after considering this edge can be this weight plus minimum distance between u and s plus minimum distance between v and t. I'm right now considering this s to u, u to v, and v to t, right? And the other possibility will be s to v, v to u, and u to t. That is w plus minimum distance between s and v and minimum distance between u and t. That's what I have written over here. And for having these minimum distance, I have to use Dijkstra. And as we all know, single Dijkstra function has big O of m log n time complexity, that is e log v, right? Let's see the brute force solution for this problem now, where for each edge of this type u v w, where u is just edge of 0. Basically, we are storing edges in the form of vector, that's why u is edge of 0. E of 0 basically, and V is E of 1, W is E of 2. So yeah, let's say I'm applying Dijkstra from U to have my distance 1 vector, and Dijkstra from V considering V as a source element, and after that I am having distance 2 vector. Then path 1 will be W plus distance 1 of S. Basically, this is just distance of U and S and NT. And in second case, I have considered distance of D1, right? So distance of U and T plus distance of V and S, right? So then I just have to update the minimum value and return it. So the overall time complexity for this type of solution would be I am iterating for each edge. So I am having M multiplied with, I am applying the extra for each U and V for each edge, right? So multiplied with M log n. So overall time complexity would be 2m square log n. And m is up to 10 to the power 6. So overall time complexity will be 10 to the power 6 multiplied by 10 to the power 6 multiplied with log of 10 to the power 6, which will be over almost big of 2 into 10 to the power 13. That would definitely give us TLE. So I have to think something else, right? Let's try to observe something. Okay, so in optimal approach, as we have observed that for each edge, we just need the distance of that U and V with S and T, right? So, and as we know that graph is a directed, not directed, graph is an undirected weighted graph, right? So distance between these two nodes like S and U, we have calculated this distance by applying Dijkstra on this node, and then distance of this S would store the minimum distance between U and S, right? And similarly, we have calculated for V also. Then, to optimize this thing, we can calculate the extra. We can evaluate the distance vector only by applying the extra algorithm on this source and destination only. Because after applying these two Dijkstras, we will be having two distance vector d1 and d2, and by these two d1 and d2 we can have a minimum shortest path from S to any node and from T to any node. Like I'm just saying that this distance 1 of S can be replaced by d1 of U, where d1 is the distance vector I have calculated after applying the extra on S, and this will be d2 of V. I guess you all got my point. So this is just a simple observation and optimization for this problem. So let's now quickly see best approach. So firstly, I have to find two distance vectors, distance 1 and distance 2 after applying this Dijkstra on S and T. Then I have to consider all edges of kind U to V with weight W. Find path 1 where path 1 is W plus distance 1 of U plus distance 2 of V. Similarly, path 2, W plus distance 1 of V plus distance 2 of U. Updating the minimum path, and just return it. Okay. So the overall time complexity for this particular solution would be twice of m log n for two Dijkstras and big O of m for considering each edge, right? And space complexity would be n plus n, which would not give us TLE, right? Let's quickly see its code now. I have already coded this part to properly utilize the time. So I have taken n, m, s, and t. N is the number of nodes, m is the number of edges, s and t are the source and destination. I have taken these as input. Then vector of pair. This is just a standard adjacency list I have prepared for each node. Sorry. And then this is VVLL is just vector of vector. I have stored the edges as well. I have taken input in the form of u, v, w, and I have stored edges of I as u, v, comma, v, comma, w. Then adjacency of u dot pushback v, comma, w. Then adjacency of v dot pushback u, comma, w. Then I have implemented the Dijkstra algorithm using lambda function, so that basically I have avoided to pass multiple arguments. That's why I've implemented it using lambda expression. So I have initialized the distance vector for each node by positive infinity, that is 1 is 17. This is basic Dijkstra only. Distance of source equals to 0. Then I have created the max type, not max type, min type priority queue. Priority queue dot pushback dot push 0 comma source. Then just basic Dijkstra stuff and return the distance vector. Then distance from source and distance of t. This is just distance 1 and distance 2, which I have discussed in one note, right? Then I have initialized the answer vector for each for each edge with -1, and now I'm considering all the edges. If this was the pruning part, if let's say distance from S, I'm considering distance from S, like if distance between S and U is 1 is 17, or distance between uh, T and V is 1 is 17. Wait a second. There is some error in this. We recheck this condition. Yeah. So yeah, it was correct thing. Basically, I am checking if distance from S, like distance between S and U is infinity. That means if S and U are in different component, or T and V are in different component, or the vice versa case. If this is the case, then there is no need to consider that edge. That means I can never include that edge in a shortest path from source to destination, right? Otherwise, I have just calculated that same thing which I have discussed. Path 1 as like d1 of u plus w plus d2 of v, and part 2 as d1 of v plus w plus d2 of u, and I have just stored the minimum of this inside my answer vector and just printed that part. Let's quickly run this. This was the sample test, right? So 6, 6, 6, 5, 12, 12, 5. I'm getting correct solution. I'm getting the correct output, sorry. Let's try to submit this now. We should get accepted. Please get accepted. Let's see. Out these 26 test cases, how many got passed? Yeah, it got accepted. Let's quickly re-summarize this problem. Basically, this problem was not that difficult. You can see this problem is easy to medium problem. Many of you have tried the Dijkstra in this problem, but maybe some of you got DLE because of brute force solution. Basically, this problem was like we are having a graph that can have multiple components, and we are having a two nodes, source and destination, and we have m edges, right? We, for each edge we have to print a number that represents the shortest path from source to destination, after considering that edge be the part of that that shortest path. Otherwise, if there doesn't exist any path, so any shortest path after considering that edge, then we have to just print the -1, right? So for this solution, for this problem, we have used the Dijkstra algorithm to find the minimums, to find the shortest path between source to u, or you can say source to v, and also t to u and t to v, so that we can consider two paths like this: s to u, u to v, v to t, and other possibility can be s to v, v to u, and u to t. Why we have considered this u to v edge as u to v and v to u into different sense, because this is an undirected edge. I can go from U to V as well as I can go from V to U, right? So I have considered both of these. In brute force solution, I was trying to do Dijkstra for each U and V for edge U to V. But in optimized solution, I have used Dijkstra from source and destination only, and I have calculated this distance 1 of S and distance 2 of T using that two distance vectors. This was just simple application of Dijkstra algorithm. This was all about the problem 3. Let's quickly proceed to problem 4 now. For starting this problem, I would say like this is a difficult problem involving DP and tree concepts, right? So if you are not able to think in that way, like how the solution of this problem works, that's totally fine. But try to learn different ideas so that you can apply those ideas in future also. Okay, so the problem was Supreet goes back to the future. Let's read this problem. While wandering around Prayagraj, Supreet stumbles on abandoned T. Lauren DMC 12 basic storyline. Uh, okay, basically, Supreet plans a few time travel trips with his best friend Sahil, and Sahil gave him a task in which he need to know, in which he now needs your help to calculate the minimum amount of fuel required for these trips. Okay, basically, Supreet is going for time travels, and for each time travel, he needs to spend some amount for fuels. Okay, and we need to minimize the total amount of fuel required for all the trips. Okay, details. The time periods are represented as undirected acyclic graph with n node. Basically, okay, let's say Preet was doing a time travel from 20th century to, let's say, 21st century, or let's say from 21st to 22nd century to the century of Doraemon. Let's say these are the time periods, and like problem says that time period is represented by n nodes from 0 to n minus 1. Okay, and you are given 2D integer array edges of length n minus 1. Okay, there is a catch in this problem. It is saying the graph is undirected acyclic graph. Okay, and this graph is having n minus 1 nodes, and we all know that if undirected acyclic graph is having n minus 1 nodes, that means the graph is tree. We will use this concept in building our solution. And for each time period, basically for each node, we are having a fuel cost represented by array. Okay, fuel of I is just fuel cost for ith node. Okay, and fuel cost for the path. Let's say if I'm going from U to V, then W, and then Z. This was the path, and for this path, the total cost would be the sum of fuel cost for each node. Okay. And additionally, Sahil told Supreet that he can choose certain time periods to take a break. Okay. Additionally, oh, this is just repeat line. If Supreet takes a break in a time period, the fuel cost of that period is halved. Okay. And second condition would be, it says that Supreet cannot take breaks in two consecutive time periods. Okay. As his friend might tease him. Okay, so Preet will have to choose break before starting his adventure since the time machine needs to be configured. Okay, this is a large problem. Let's try to understand this problem in short key observations, and we have to minimize the total fuel cost that Supreet needs to complete all the given trips. Okay, okay, and we need to output that minimum total cost with mod 1e9 plus 7. The constraint for n and k is 4000. Basically, the problem is saying the guy Supreet is doing k time travels from source to destination, where S and D are the time periods and represented by nodes. Nodes are numbered from 0 to n minus 1, and the half is actually a tree with n minus 1 edges. This is the given data, right? Yeah, as n minus 1 nodes, not nodes. So this, right? So it's tree, and for each node we have fuel cost, and for a path, total cost is summation of fuel cost of all the nodes in that path, which I have already described. I need to minimize the total cost of all trips and then take mod with 1e9 plus 7, right? Also, I can have, I can have the cost of some of the nodes that are not consecutive. Okay, I have to decide all those nodes where to take break, like where I should have this cost before the trips, right? This was the problem. So I have considered the sample test given for this problem. So the sample tree is something like this: 0, 1, 0, 2, and then 1 to 3 and 1 to 4. This was the fuel array, and trips were 0 to 2, 3 to 2, 4 to 3. Let's consider all those trips 0 to 2. 0 to 2, so pre would go from 0 to 2. And for a trip from 3 to 2, so preach would go from 3 to 1, then 1 to 0, and then 1 to 2. And for trip 4 to 3, he should go from, yeah, he would go from 4 to 1, and then from 1 he would reach 3, right? So overall, let's, after after seeing all these trips, the overall thing, we can observe that overall Supreet visited node 0 two times, once in this strip, one another time in this, secondly in this strip, and he visited node 1 two times, firstly in this strip, secondly in this strip, node 2 in node 2 two times, firstly in the here and secondly here, node 2 also two times, and node 4 also one times, right? And we have to find the charger, yeah, and we have to minimize the cost, total cost, right, of all these paths. So I have visited all these nodes these much times. So the effective cost array would be like 2 times the cost of 2, 0, 2 times the cost of 1, 2 times the cost of 2, 2 times the cost of 3, 1 times the cost of 4, which will be this 2 into 3, 2 into 2, 2 into 4, 2 into 5, 1 into 1. So this would be the, this will be the effective cost array for me, for Supreet. Uh, and now the question has changed. Now the problem has changed to find the medium sub of all the array elements such that I can have non-adjacent nodes. Not, yeah, this is the problem. And if you have worked on, like if you have solved some sort of DP problems, you can easily configure that. You can easily find out that this is a DP problem now. Basically, this you can say a kind of pick non-pick type of DP where we have to consider like this. If right now I am at this index, I can do something like this: DP of index can half or not, like DP of I comma 0. If I can't half, then take the cost as it is and go for the neighboring part. If I can half, I have to consider both this. Like, let's say if I haven't, let's say if I am not halving this, I'm not uh, taking the half cost, like original host plus neighboring part. Otherwise, I can take the half cost plus neighboring part, these two, and I have to take the minimum out of these. Some sort of DP like this, like because there are overlapping subproblem, we have to use the DP. Let's try to build a DP state. Let's say if I'm taking DP state something like this. Okay, DP of u comma can half. This this can have only two values, 0 or 1. So dp of 0 comma dp of u comma 0 will be the minimum sum of all elements in subtree rooted at u. Basically tree was unrooted, right? Such that I can't halve the cost of u, right? So this is something which I am storing in dp of u comma 0, and in dp of u comma 1 I am storing the minimum sum of all elements in subtree rooted at u such that I can halve the cost of u, right? So for this type of dp, the solution, the final subproblem would be dp of 1 comma 0, because I can take any node as a root. Let's say I'm considering node 1 as a root, and initially I can halve the cost because uh, I have not considered the adjacent node at that point of time, right? So I can take the half cost. So this will give me the final subproblem, the final output for this problem. Let's see the transition right now. Let's say if I am having these type of edges u to some v1, v2, v3, and many more children, right? So dp of u comma 0 equals to, I have to consider the original cost of u plus, then I have to consider the cost for substituted at its children, right? I have to consider these subtrees. So if I have not halved the current node's cost, that means I have the chance to halve the cost of its children, right? So that's why I have taken 1 over here. So dp of u comma 0 should be cost of u plus summation of dp of v comma 1, right? Whereas dp of u comma 1 is equal to, if dp of u comma 1, like I can halve the cost or I can't, like either I can halve the cost or I cannot halve the cost, right? I can consider both of these cases. First case, I'm not taking the half cost, and in second case, I'm taking the half cost. If in first case, if I'm not taking the half cost, uh, I have the chance to have the cost of neighboring child, right? And if I am considering the half cost, then I don't have the right to have the cost of neighboring child, right? So let's see the overall algorithm. For each step as to the association, I am doing DFS to find the frequency, or you can say the visit count for each node. For this, I have to uh, run DFS for each query, right? Not each query, for each trip, and the number of trips are k. So the overall time complexity for this step should be big of k times n, right? And after having the visit count, I have to calculate the effective cost array, which I can calculate in big of n. Then I have to apply DP, right? And DP will be just 2n, because DP also I have to consider DFS starting at 1, right? Then I just have to return answer percent with 29%. So the overall time complexity for this solution would be big of nk, which is 4000 cross 4000, which is overall which is almost equal to 1.6 into 10 to the power 7, and the space complexity would be big of n. So let's quickly see its code. As I have already said that, yeah, this problem is a hard problem. So if you are not able to think any step on your own, it's totally fine, but try to understand the solution. I have implemented this function first, bool travel, in which I am considering source and destination of each trip. I have taken bool value so that I can return whether it is possible to like whether it is possible to reach that particular destination starting from that source or not. But this can be redundant because it is a tree, and from each node I can reach any other node. So answer will be true in all the cases, but no. For the sake of generality, I have implemented in this type. Okay, so this travel function is taking arguments like node, its parent, the target node, then just adjacency and visit count. If node is equals to the target node, that means uh, I have reached the target node. I have to return true and just incremented the frequency of node, current node. Initially, if bool value is false, I'm iterating for each neighboring children of which is adjacent to current node. If neighbor is not equal to parent, I have to uh, update the found value, like found of or like found equal to found or travel of neighbor. This is just simple DFS. And if found equal to true, I just break the loop. If found was true, just increment the node frequency and return the found value. This function, like, you can implement in different manner also. This function is used to just calculate the frequency, or you can say the visit count for each node. Let's see, like, this was just input part. I have taken n as input, then edges of size n comma n minus 1 cross 2 2D array, taken input. Then I have taken fuel array, k, all the time travels. Then I have built the tree. This is just standard graph building using adjacency list. Then I have, for each trip belongs to that time travel, I have uh, I call the function travel starting from that source trip of 0, and its parent I have considered as -1, and destination as trip of 1. This is just passing arguments. And then this is just, this cost vector is effective cost, which I have discussed in where running the travel function for each trip. I have updated my visit count. Okay, so I have evaluated the effective cost here by multiplying the visit count with the fuel value of that node, and this is just a modular part. I have taken mod with 1e9 plus 7, then 2d dp, and let's quickly see the implementation of this recursive function for dp. I am taking current node as input, its parent, can half, and this is just passing arguments. If initially I have initialized the minimum value as positive infinity, I have like no half current node price. Basically, if I am not halving the current node cost, so the cost would be cost of node, and then just iterating towards iterating its neighbor. If neighbor is not equal to parent, I have updated the uh, no half current node price. No half current node price is basically when I would use this thing when I can't half. Basically, when can half value is 0, right? I have incremented this thing with minimum price I can get in the subtree rooted at this neighbor. And as I am not halving the cost at this current level, I can half the uh, cost for the neighboring node. This is just modular part. And secondly, I have also calculated if I am halving the current node. If I am halving the current node, I have checked if I can halve the current node price. Then I have updated this thing as cost of current node by 2. Then I have uh, added for all the neighboring nodes. If neighbor is not equal to parent, I have updated this cost. I have incremented the minimum price for subtree rooted at neighbor. As I am currently halving the cost, that's why I'm not leaving a possibility to half the cost for next neighbor, right? This is a small part. And at the last I am returning many of these two after taking mod, right? And the final sub problem was this was the sample input, right? There's some issue. Let me reload the page. Okay, it was 5, then 0, 1, 1, 4, 3. This was past it. Yeah, 0 to 2, 3 to 2. Let's run this code now. 26. Output should be 26, right? Let's quickly submit this code. There are some wrong answers. Check where I'm wrong answers. Wait. Should be 0 or something. Oh, sorry, yeah. For the final subproblem part, I have to consider any of the source from this time travel part to the root, because otherwise the parent part would give me some errors, I guess. So for final subproblem part, the answer should be, they should not be 0, there should be some, let's say I'm considering trip zeros source, right? So let's time travel, it's time travel, right? Time travel, this should work. Yeah, got accepted. Okay, so we re-summarize the problem. Basically, the problem was that Supreet is, yeah, Supreet is the guy who is going to take K time travels, and on this particular tree, given tree, he can have some of the costs of nodes which are not adjacent, right? Which he have to decide before taking the trips. So I have just analyzed all those trips and considered the frequency of visiting all the nodes. And after multiplying that frequency with the actual fuel cost of each node, I am having all those uh, values which we have to add in the overall fuel cost of all the trips, right? In which I can have some of those costs which are not adjacent to each other, right? So this was the problem, which was finally turned up to be a TP problem, in which I have uh, from a DP state something like this: dp of u comma can have, and with which dp of u comma 0 was minimum sum of all elements in subtree rooted at u, such that I can't have the cost of u, whereas dp of u comma 1 was minimum sum of all the elements in subtree rooted at u, such that I can have the cost of u, right? these were the transition part, and overall time complexity for the solution was k times n, which is up to 1.6 to 10 to the plus 7. And final subproblem for this was dp of trips of 0 comma 0 comma 1, because I can have, right, percentage 1e9 plus 7. So this is all about the expanding horizon 6.0 solutions. If you are having any kind of doubt in any of the problem, it be like it can be problem 1, problem 2, problem 3, or problem 4, you can ask in comment section or anywhere. Okay, so that's all for today's video. Bye bye.